Hello everybody, thank you for attending RSA webinar today. My name is Artur Kosakowski and I will be running today's presentation together with my colleague Rafał Gawenda. The topic of this webinar is instability warnings during model calculations, causes and solutions. In this webinar, we will focus on instabilities reported during static analysis of a model in a robot. The webinar will be the combination of a slide presentation and live use of robot, followed by Q&A session. As the microphones of attendees are muted, please submit your questions using the question box of the GoToWebinar panel. The webinar will cover types of instabilities reported in robot, reasons of instability warnings, how to check if the reported instability can be ignored, frequent mistakes, tips and tricks. The topic of the next webinar will be API and macros in robot. We have decided to make the webinar on the instabilities because it is one of the most popular topics on the robot forum. As you can see on the slide, there has been already about 600 posts on this subject there. The examples demonstrated during this webinar are based on these posts, and we hope that it will allow you to avoid running into such situations and solve them where they actually happen. Let me start with explaining what types of instabilities can be reported by robot. Type 1 is zero-value element on the diagonal of the stiffness matrix. Type 2 is zero-value element on the diagonal of the inverted stiffness matrix. Type 3 is the ratio between the maximum and the minimum values on the diagonal of the inverted stiffness matrix being higher than the predefined limit. This limit is set as approximation 1 to the power of 13, but it varies depending on the selected solver. It can be caused, for example, by large difference in sizes and lengths of elements of a model, but also can be reported for a model with excessive releases. Knowing the types of instabilities, we may have a look at their reasons. The common error, especially when one starts using robot, is the selection of a wrong structure type. These types should be understood as the way of reducing model size, number of equations to be solved, by elimination of some degrees of freedom rather than kinds of structures, especially when you are about to decide between truss and frame models. Mind that all connections for the prior are assumed as pinned, so any missing posts or diagonals will result in the instability warnings. Let's have a look at the example where an electricity transmission tower was defined as a 3D truss model, whereas it should have been a 3D frame instead. So this is the example of robot. If I calculate it, okay, you can see that there is the instability reported for the vertical direction. And if I ignore that, you will also have the 360 error at the stage of the model analysis. If I go to the geometry and I change the model type from 3D truss to 3D frame, I can calculate the model, okay, with no instabilities along with model analysis, but the difference is now that all the connections are treated as fixed with bending moment transfer. So in this situation, I need to define truss bars, the elements that cannot transfer bending, and you can define truss bars for these short elements here, but for the elements that are built from a chain of elements, you cannot use truss elements. That will result in the instability, so you should define releases instead. Okay, so in this case we go for fixed pinned. I will remove the rotation. I will block the rotation about the own axis of the profile, and in this case I can apply the releases in such a way that I have a pinned connection of the diagonal here. And now, of course, I can run calculations. There should be no instability reported. Okay, so let me go back to the presentation. I selected this structure as it makes a perfect example for understanding the difference between a truss being a structure type designed for transfer of axial forces with the assumption of no bending moments and available degrees of freedom for selected model type. As for this kind of structure, we have to select a frame model for the column, as the columns are intended to transfer bending. We have to make sure that the roof trusses are modeled in such a way that they do not fall apart moving sideways. In other words, the chords should be modeled as continuous elements, whereas the posts and diagonals can be defined as the truss bars. Let's have a look at this model in Robot. Okay, if I load this model, if I attempt to calculate that, I will have, again, a bunch of instabilities reported, and of course, incorrect results. Yeah, so I'll terminate that. What is the reason for that? The reason is the definition of truss elements. Okay, let's give a robot a bit of chance to refresh. Okay, so I'm going to display attributes of bars, and you can see that all elements of trusses are declared as elements with pinned ends. So of course, this can move sideways. So the correct way of modeling such structure is to, let me open the corrected model. Okay, so I will display again bars, truss bars, and I will also display releases. It's okay. If we have a closer look, we can see that only posts and diagonals are declared as truss elements, chords are continuous, and the releases are applied at the connection between the trusses and between the trusses and columns. Of course, if I calculate this model now, there should be no instability warnings reported. Okay, so let's go back to the presentation. Investigating the reason for instability in the previous model, I said that truss chords should be continuous. This is the explanation why. If you apply releases to all bars meeting in the same node, you make it sort of detached from the model, and it can rotate or, depending on the releases, move outside of the plane of the truss. If you consider bending moments in chords being too large, you may apply partial releases for these bars instead. In many cases, an attempt to release all rotational degrees of freedom results in bars rotating about their own axis. The effective way of checking if this is the case is to redefine releases so that Rx rotations are blocked. If this causes excessive torsion, you may restore the original releases in the locations that are needed, or use partial Rx releases instead. Let's see this on the example, which will also illustrate the fact that the instability detection for fastest solvers is not always as accurate as for the slower ones. So if I go back to the robot, Okay, I will open another model. Okay, this is this structural roof. And okay, if I calculate the model, I've got the instability for the horizontal direction, which at first glance doesn't look justified. So if I go to job preferences and if I go to structure analysis, I mean, by not justifying means that you may say that, okay, this is probably the numerical instability, so I can ignore that. But before that, let's change the solver to Skyline. And then when we calculate the model again, the detection of instability changes, and now we have rotation reported. So if we have a look at this node, okay, so we can see where the rotation instability has been reported, and we can also display releases, okay. So if we have a look at the releases, we can see that this is the situation where you may suspect that there is a likelihood that too many degrees of freedom has been released, especially in the nodes where all the bars have got the releases. So let's delete the releases not used in the model, and then we make the change. We modify the releases, blocking the rotations about own axis of the profile, and then if we calculate the model again, there should be no instability reported. Of course, now if we block that rotations, then we may have a look at the results. We may go to the forces and actually go to global extremes and check what are the values of torsional moment. They are very small. But in the case when they are larger than you accept them, you may, as I mentioned, restore the releases or use the partial releases for this degree of freedom. Okay, so let's go back to the presentation. Another cause of instability may be the excessive use of linear releases. Such situation often happens with the attempt to model masonry walls as shown on this slide. So the concept is no tension in the walls, so we apply the releases, but actually you should not apply releases for both panels along their common edge. Next reason for instability can be lack of in-plane stiffness of surface elements, which can be seen for panels with pinned linear releases defined for all edges. In such case, there is a simple solution, which I will demonstrate on the simplified opening robot. So I will go back to the program. I will open model. Okay. So we have a slab supported on the columns. The slab is built from number of panels. And okay, let me switch off meshing. So in this file, we have already solved the instability problem by applying additional supports. So what I'm going to do, I'm going to support the nodes, which I have this RZ supports defined, and to demonstrate the selection options in robot, I will select now finite elements by these nodes, and I will select panels by selected elements of the mesh. Okay, so we'll open that in a new window, and then I will show the linear releases. Okay, so we go to model and we will display the releases. Okay, and we also add the display of codes, so that, okay, so you can see all the edges are defined as being simply supported. And if I now open the support dialog, and I will again select the RZ supports. I can delete the supports defined in those nodes, and when I calculate the model, we'll have the corresponding instability warning. Okay, there's a rotation about the global z-axis of the coordinate system. Okay, and if I now restore the supports in those nodes, okay, I can calculate the model with no instability warning. Okay, so let me now select all the simple node cases, and I will select those nodes again, because if I apply the supports, I'm curious what is the value of a bending moment, or torsional moments in those supports. I mean, so if I go to reactions, I filtered the table by this selection, limited only to those nodes, and we can see that these values are zeros. So, okay, the supports do not transfer any unintentional torsional moments. Okay, so let me go back to the presentation. Sometimes it is just enough to zoom in at the location of the reported instability to find out what went wrong. Often it is just a missing snap, which is easy to correct by moving a node to the right place, as happened for the model attached to this topic on the robot forum. More often than having a detached element, the lack of accuracy in modeling causes generation of very short calculation elements instead. On this slide, you can find the steps which should allow you to determine if this is the case for your model too. Let's apply this procedure to a model where this actually happened. So let me go back to robot. Let me load another model. So, okay, I will try to calculate this model. Okay. So if we have a look here, I mean, there is no apparent reason for instability. So as previously, okay, we may have a look at the releases, okay, and what we can do, we can delete all of them, see if this solves the problem, if releases are the issues, and as you can see, no. So we have to look for something else instead. So what I'm going to do, I'm going to select all the model, and I'm going to use the intersection. And now, if I open the bar table on the values, and I sort by length, I can see that we have a bunch of very, very short elements. And this, of course, is the issue for instability due to the very large difference of the stiffness of elements of the model. So, okay, if we go here, maybe, and then let's select those bars. Okay, we can transfer this selection, and if I have a look at the model, okay, I can see where these elements are, and if we zoom, we can see what the problem is. So, okay, let me reload the original model with releases, and now I am going to use the detailed correction option. I need to adjust the model, so I will select the planes. Adjusting to the plane, I will indicate first the vertical, and then the horizontal planes. And now if I calculate the model, there should be no instability reported. Okay, so we have this zero length part doesn't exist. I mean, this is just a ghost from the initial verification. If we go to the analysis and the verification, you can see that those nodes that defines these elements were merged during the model generation. So we have a correct model. We have the model with the releases and no instabilities. So right, so let me go back to the presentation. For models with surface elements, the same situation may happen when you have poor meshing. In such case, generating a more regular mesh should be enough to solve this instability issue. So if we go back to robot, and okay, let's load another model. If I display meshes, you can see that those nodes create again very short calculation elements, dividing these beams into very short elements, and that's most likely the issue for the instability. So what I'm going to do, I'm going to check if that's true. I will set the smaller elements and I will get rid of the regular meshing. And now if I mesh the structure, okay, I have a more regular mesh, and if I calculate the model, there should be no instability. So in this case, you are able to determine that that was due to these very short elements because of the meshing with very small elements at the intersection of the beams. So right, okay, let's have a look at another situation. Very often, the instability is caused by missing restraints in supports, especially for degrees of freedom that doesn't correspond to any of applied loads. So they are considered as being not needed. The good example is the structure shown on this slide, where somebody forgot about rotations as only vertical loads were defined. The same situation may be caused when all adjoining elements have got rotational releases defined as shown on this slide. Releases defined for the other beams and columns cause the rotation of bar 1267 about its own axis. The common cause of instability reported for a frame model with large number of simply supported beams and pinned supports are rotations of columns about their own axis. The simple solution is to add RZ restraint at the supports, as for these types of structure, column-based connections will not allow for such situation anyway. So let me again load the model in robot. Right. So if we calculate the model and have a look where the instabilities are reported, which is the top of each of the column here, we may focus on the definition of the supports. So we have a pin support. We can check what will happen if we block the rotations about the own axis of the column, and well, that solves the problem. Okay, so if I go back to the presentation, that's going to be another situation. The lack of horizontal restraints for raft foundation may lead to both instability warnings and lack of convergence for elastic soil with the uplift. Despite having only vertical loads for a shell model, you need to provide horizontal restraints. For example, some elasticity representing friction, which can be defined as either elastic soil or nodal supports. So, okay, let's have a look at the real example. Okay, so we have a situation that the foundation was defined originally with no nodal supports. So if we go here and if we first of all delete all the supports that are not in the model. So I'm going to delete all the nodal supports. So this is the model as it was originally defined. And then when we attempt to calculate that, we have the problem. First, there is instability warning, and then, of course, the nonlinear analysis results with some suspicious results because we do not expect that this structure loses its stability. So if I have a look at the supports, I define the supports with very small elasticity values for the horizontal degrees of freedom. And if I apply that to all the nodes or selected nodes of the model, there should be no issue. So there is no instability, and of course the nonlinear analysis, which is caused by uplift of the elastic soil applied to this panel, converges with no issues. Okay, so let's go back to the presentation, the slides. The similar principle applies also to frames, for which the results at first glance suggest that the reported instability can just be ignored. So let's see that on the example. So if I load another model, and if we calculate this model, there is the instability, but if we have a look at the results, there's nothing wrong here. There are very small values, so we may say, let's ignore that. Let's press this escape button. But before that, you may have a look at the model. You check the applied releases. So we have all the connections are pinned and all the supports pinned, which is a bit suspicious. So if we can run a test scenario, we can define the new case. Within this new case, we can apply a very small load, being, for example, 1 kilonewtons in each of the horizontal directions, and we can apply that to any node. And when we calculate this model again, we have the instability reported as previously, but you can see what will happen with the displacements. So definitely, either you need some bracing or you need different support conditions for this model. The instability can also be caused by missing properties of a bar section. In the situation as on this slide, in order to calculate the model, robot assumes default value of Ix being much smaller than Iy and Iz, which results in the big difference of elements of the stiffness matrix. For panels with orthotropic thickness definition, you should be careful with the settings of its my direction. It cannot be defined as perpendicular to the panel, therefore the suggested approach is to use the automatic direction and set the local X of the panel in the right way, rather than indicate it as linked with the global coordinate system. Let's see on this example. Let's see this on the example, which has got yet another instability reason. So I will open robot. Let's load this model. Right. It's okay. If I calculate the structure, get the instability reported. So let's have a look where this instability is reported. Okay, I here can see a bunch of nodes. So what I'm going to do again, I'm going to see which surface elements are attached to those nodes and which panels they are from. So if I open that in a new window, I can display the descriptions, so I can see the definition of the thickness labels. So let's have a look at this thickness labels. So we have 1900, so which is direction X, which is perpendicular to the panel, right? So we set it to automatic. And we have 300, so let's have a look. And it's the same story. So we redefine that to automatic along local X of the panel. Okay, so now I will calculate this model again. Okay, so I've got another instability, but no longer any issue with those walls. So if I have a look at the whole model and I select the instability, so I can see that this is reported at the connection of two bar elements. So let me select those bars elements by node, and node number is 618, so I can select that. I will open that in a new window and check if there are any releases defined for these beams. Yeah, so we have clearly a mechanism, so we cannot have a pinned connection in these nodes. So first of all, I'm going to redefine the connection. So I will redefine the releases, and in addition I will block the rotations about element own axis, and then I hope that that should solve the problem. Okay, so we have no instability reported. It's okay. Let's move to the presentation again. The instability can also be caused by incorrect definition of material properties, and you can check the properties of the material adding this material properties columns in both bars and panel tables. The use of air links increases the difference of values of elements of the stiffness matrix, which may go above the limit for given solver, which, as has already been explained, results in the type 3 instability. Such instability can be ignored, but only after determining that this is the case. As MKL and SPAR solvers always use R-links elements to model rigid link connections, you may try to check if the Skyline solver reports the instability as well. So let me show that on the example. It's okay, so we have a situation that bar elements were used to represent walls and to indicate that this is really not a point connection, but connection along the entire wall edge. Rigid links were defined. So if I calculate a model, I got the instability, which, okay, looking at the definition of the rigid links and the supports, seems like unjustified or being just a numerical value. So if I go to job preferences and I change the solver to skyline so that I could switch off the use of rigid links, when I calculate the model, there is no instability reported. Okay, this is also the very often question. Okay, I've got the instability reported. What is the cause, and can it be ignored? So let me demonstrate the steps we take to determine what really the cause of the instability is, and the verifications that you may do to make sure that this instability hasn't got any negative impact on the obtained results. So I will switch to robot again. I will load another model. So for better accuracy of the analysis, I set the solver to skyline. We sacrifice the speed for the sake of more precise detection of instability. And you may see that that's maybe something to look at first, I mean, earning elements, but as these earning elements are used for rigid links which have supports in slave nodes, I cannot simply switch it off because I have to use rigid links for such model. But I will first calculate the model and look at the instabilities rather than try to switch links as a first attempt to determine the cause of the instability. Well, these Erling's elements cause the stiffness matrix to be poorly determined. That increases the calculation time. But as I said, I prefer to have a more accurate detection of instability in the situation I'm not sure what is the cause, than have a faster solution. Right, so we have the instability detected. In node 514. So what I'm going to do, I'm going to, because the time of calculation is not that fast, so one of the ways of speeding up the analysis is to see, okay, so what I'm going to reduce the model. I will delete all the floors, but the one where the instability was reported, and okay, I will get rid of those rigid links at the bottom of the columns. So okay, we delete this master node, and then I will replace the bottom part of the model, the stories that I deleted, with the equivalent supports. Okay, I will use fixed supports, and I will see if the instability disappears. It doesn't. Okay, so that means that I should have a closer look at this floor, and I will switch off the display of rigid links for a moment. And instead, I will have a look at the defined releases. Okay, so we may want to have a look at the model, and again we may say, okay, that may be that the instability may be caused by excessive releases, by the release of certain degrees of freedom. So if I have a look at the definition of the releases, I may see what will happen if I block the rotations about on axis of the profiles. So okay, I made this change, and I will calculate this model again. Okay, so now I've got the instability, but this instability is in a different node. And if we go to the results and we have a look at the displacement, we can see that the values are really not that big, okay, for combinations. So that may be the solution. So let me load the model, full model again, and think that I should have started. Okay, I will calculate this model again as it is, because I overlooked one point that is really important. So when you start the analysis, when you calculate your model and you have the instability reported, of course the first thing to look at are the displacements and rotation of the nodes. Of course, I know that they are excessive, and that was the reason I looked at the floor where the instability was reported. But I mean, the reason I look at that floor was what I'm going to show in a moment. Okay. So if we go to the results and we display the displacements and we go to global extremes, you can see that that was the reason I decided that I have to have a closer look at the location of the instability. So we modified the releases which solved the problem for this floor. If I mean the same value of rotation will be for this model with a single floor. That will not happen. That will not change unless till the moment I modified the releases. So I'm going to do the same. I'm going to modify the releases for the whole model and see what values of rotations and displacement I will have. As you remember, the objective is to determine whether we can ignore the reported instability or it has got a negative influence of the results. It cannot be ignored, meaning that we need to introduce some changes in the model itself. So let's have a look whether we still have got this huge RY rotation, or if we manage to solve that by redefining the releases. Okay, so we have the instability, but this time in node 99 on the UX direction. So this is something different. Let's move that away for a moment. Let's have a look. So, okay, this problem has been solved. Well, you may say, okay, so we may want to, okay, I will display that, okay, for all combinations. So we may say, okay, I may ignore that, but I mean, looking at the results, I can see that there are still values of rotations and displacement that are much higher than I would like them to be. So let's have a look at this node and this direction of instability first. So if we select node number 99, and okay, let's as in the previous example, let's define a test case. And for this test case, let's define the test load, a very small load on the direction of reported instability, so X, and we define this force in node 99. Okay, let's have a look where it is in the model. It's okay. So we can see that this is for bracing. So we may want to select these bars by node. Okay, let's have a look. And we will display the sections. Well, okay, see this is a flat bars. So for the sections, okay, the sections are named BR. Let's delete the sections that are not used. It will be faster to find the right one where we have this BR. Okay, over there. So actually, the flat bars are defined as the I section type, but are still flat bars. So okay, I will calculate the model again. And this time, the objective is to look at the results for my test case scenario. I want to see what will actually happen with the displacement of node 99. Okay, so we get the results now, and in the results, if we go to to the displacement table, we can limit the table to node 99, and you can see that actually this is pretty large horizontal displacement for this node. So that suggests that actually either these elements should be defined as tension only, or they should be more stiff. So let's redefine the sections for these flat bars. Let's define them as I-beams. Okay. And now, previously I also focused your attention on the fact that we have relatively large displacements for vertical displacements. And looking at the sizes of the beams, usually to reduce the vertical displacement, we have two options: either increase the size of the beam or look at the connections between beams and columns. So I do not want to increase the size of the beam because they are already quite large. So instead, what I'm going to do, I'm going to have a look at the releases, and I'm going to say that it is highly unlikely that there is a fully pinned connection between the beams and the columns. So I'll go to Elastic tab and I will define the partial stiffness for vertical rotations. Okay, let's redefine the releases. And I believe that represent the real support conditions a bit better, more accurate. Okay, so we made these two changes, and now we are going to calculate our model once again. So after calculations, what I'm going to look at are the horizontal and vertical displacements. First of all, I do not want to see this 90 millimeters for bracing, and I want also to have a smaller value for vertical displacement for the beams. So that was 88 millimeters or similar value. So if we go to the displacements, as you can see, there is the instability is no longer reported in node 99 as previously, so that's a good sign. So if we have a look now at that, we can see that okay, the values are smaller. That's what I wanted to achieve by defining the elastic releases, and we do not have for horizontal UX degree of freedom. We do not have this 99 millimeters of displacement for the bracings. Okay, so this looks fine, but if we have a closer look at our axis rotation, this value is still larger than I would like to see it. So if we go back to the model, and maybe I will switch off these rigid links again, or maybe not. Maybe I will keep the rigid links. So I'm going to have a look at this beam here. So, okay, so we have the instability here reported in, okay, so I will select, and I will select a bar by node. Okay. So, okay, I've got the situation in this model, and I will switch off rigid links. That's okay. So I have a beam here, which sort of stabilize this large parallel to the x direction beams at the top floor, and I don't have those beams for these three levels. So what I'm going to do, I'm going to copy this beam okay, and I will calculate my model again, and this time the objective is to reduce this suspiciously large rotation, Rx rotation. So I hope that's going to be the last modification that I need for this model to keep all the displacement and rotations within the targeted range, having the reasonable values that I would like to see. Okay, so we have still the instability reported, but let's have a look what we achieved for rotations. So, okay, so if we finally find all the values to be as we expected them to be, then we may see if there is finally the reason with the instability are these R-links elements. So we can switch off R-links and then calculate the model. That's the final check. No. Oh, that's okay. That was exactly the reason why R-links are necessary. I mean, we have the supports, as I mentioned at the very beginning, which of course I've forgotten about that. So I do not have to, instead of switching R-links, I need to actually delete the releases. Okay. So if I delete all the releases, I should have no instabilities reported and slightly larger horizontal displacements, because the reason for those rigid links are actually reduction of the horizontal displacements due to the stiffness of the floors. So let's have a look. After deleting the releases, the calculation time for Skyline solver should be much faster because of the better conditioned stiffness matrix, and we have no instability reported. And we may see that there is the increase of the horizontal displacement, but this is as expected. So now we may say, okay, so we solved the problem, and when we restore rigid links, we can ignore the instabilities. So okay, let's go back to the presentation. And finally, I'd like to focus your attention on typical mistakes. First of all, make sure you defined correct support conditions. Check if your block required degrees of freedom for supports, don't apply releases at free panel edges, don't treat escape button as the solution for reported instabilities. Check the results first. Make sure you have this check done before running the dynamic load cases, and the same applies to code checking models of robot. In case you think there is no evident reason for instability to be reported, you may try to use the skyline solver as we did during this presentation for most accurate detection of the type and location of an instability. As calculation time for large model may be long and you may need to repeat this process few times, you may consider reducing the size of a model by deleting some stories and replacing them with equivalent boundary conditions, which we did in our example, and the same may be done for models with triangular and trapezoidal load distribution, where you may shorten the calculation time by deleting claddings. When you use Calculation Manager for running calculations for selected models, the reported instabilities can be found in the folder indicated on the currently displayed slide. As the topic of our next webinar is API and macros, I have decided not to show this very useful macro today, but you can find it under these links. This is the Rafał's macro for finding very short elements, which for the purpose of this webinar, I found by running the intersection for the selected model. Lastly, I'd like to encourage you to use these links to learn more and find solutions for your problems. And now please free to ask questions. Rafał, do we have any questions that? Okay. So any questions? Right, so as we are running short of time, I would like to ask you to post any questions on our robot forum, which we monitor daily, and we'll do our best to answer them. And finally, I'd like to thank you all for attending this webinar and invite you to join the next one on API and macros, which will be on the 25th of January next year. Thank you for attending again.